Well, all right. So I'm very happy today to be able to introduce Joakim Nivre, who is visiting us by way of Washington, D.C., by way of Google, New York, by way of Uppsala University in Sweden, where he usually is. He's on sabbatical this semester at Google, New York, working with some great parsing people. So if you didn't know, Joakim wrote the book on dependency parsing, literally. The textbook and I think maybe some other stuff as well, monographs and lots of papers. And the probably the most popular dependency parser that there is, and certainly the most popular if you want to go parsing left to right, is MaltParser. It's the mark of a truly good and dedicated researcher when they decide to compete with themselves. And you can see from the title that now he's determined to leave himself in the dust. But MaltParser is what Google uses internally to parse the web in a week on 2,000 machines. So it's very fast and it's very effective. If you want to know anything more about dependency parsing and want to talk to somebody who's read all the papers and can keep everything straight in his head, I believe that his meetings end at 5, but his train is not till 6:05. Looking forward to the time.
Thank you very much, Jason.
I'm sorry, there is one thing that I should mention, because we were talking about it this morning. He has a PhD in linguistics, but then he went and he got another PhD in computer science. It turns out that if you do 2 PhDs, you can do the second one part-time and still finish on schedule.
Thank you, Jason. And thank you very much for inviting me. I'm really excited to be here talking about dependency parsing to such a big group of people. It's not, I think, many places in the world that you can find an audience this big for a talk on dependency parsing, so that feels great. So the general problem that we're considering here is that of syntactic parsing of natural language. And that's a task that has often been described as the task of figuring out who does what to whom given a sentence in some natural language. Like, for example, this boring example from the Wall Street Journal, economic news had little effect on financial markets. Now, over the years, a number of different approaches have been proposed for this task, both in terms of the formal representations used to model syntactic structure and in terms of the models and algorithms used to derive those representations. Now, in this talk, we'll be concerned with dependency-based representations, where the basic assumption is that syntactic structure, or at least the essential part of syntactic structure, can be reduced to binary relations between words. And this typically takes the form of a dependency tree, as in this picture, where we connect word pairwise. So, for example, there is a subject relation from had to news, and there's an object relation from had to effect. Now, this approach has a long tradition in descriptive and theoretical linguistics. Some would argue all the way back to Panini's Indian grammar several centuries before the Common Era. It's only relatively recently that they have become really popular in computational linguistics. And in fact, I mean, Jason himself is one of the persons who is really responsible for this. He did some of the pioneering work on statistical parsing for dependencies, and then it's really taken off in the last 5 to 10 years. So in this talk, I will not have time to go over all the work that's been done in the last, let's say, 10 years or so. There's been really a lot of work. So I'm going to focus on one particular approach to this task, which has become known as transition-based dependency parsing, which is kind of, in some ways, an odd way of going about the problem, because it's a fairly indirect way of tackling the problem. But it has sort of 3 basic components. And the first component is a transition system or abstract state machine. So think of finite state machine, but instead of having these simple atomic states, you have states that have rich internal structure. A transition system for deriving dependency trees, essentially. The second component is that we then try to learn a model for scoring possible transitions in this system or possible parsing actions with respect to how likely they are to lead to a good parse for a sentence. And given such a model, we can then perform parsing by searching for the optimal transition sequence, the optimal sequence of actions, or the optimal path through this state machine, if you like. Now, there are a couple of advantages of doing it this way. Jason already sort of mentioned the fact that you can do parsing very efficiently with this approach. Typically with low complexity, as we shall see in many cases, the parsing time will be linear in the length of the input, which for syntactic parsing is pretty good, arguably as good as it gets. The other advantage that you have is that in this approach is that you don't get any rigid constraints from your parsing algorithm on the kind of features we can use in our model for scoring transitions. And in particular, you can make use of rich history-based feature models for disambiguation. Now, there are some disadvantages with this approach as well, and those will become apparent as we go along. And that's the sort of beyond part of the talk, if you like. So the plan for the talk is as follows. The first part will be a relatively basic introduction to transition-based dependency parsing, where we will restrict ourselves to a transition system that can only output projective dependency trees. For now, a projective dependency tree is a tree that doesn't have any discontinuous constructions. Okay, I will make this more precise later on, where we will be performing parsing completely deterministically using a simple classifier to rank the possible actions. So in one way to characterize this is to say that this is essentially what you get if you download MaltParser, our open source system, off the web and run it out of the box without changing any default settings. And another way of characterizing it is to say that this was the state of the art in transition-based dependency parsing 5 years ago. Okay. In the second part of the talk, I will then highlight some recent developments that have sort of targeted weaknesses in this basic approach and try to do better, in particular improving parsing accuracy. Beam search and structured predictions, different techniques for handling so-called non-projective structures, that is structures where we can model discontinuous linguistic constructions, and finally some recent work on joint part-of-speech tagging and parsing. So, before we begin, just a little bit of formal notation, which will be needed to characterize these models. So, it's very natural to formalize a dependency tree as a directed graph, and more precisely as a label directed tree, where we have on the one hand a set of nodes, and the special thing about dependency representations is that we have exactly one node for every word in the sentence. So there's a one-to-one correspondence between nodes and words. So I will often sort of use the word nodes and words interchangeably when talking about dependency trees. And by convention, we index these nodes by the position in the sentence, so position of the word in the sentence. We then have a set of directed arcs, which connect sort of pairs of words, and those are labeled with dependency types. So, as I said before, we have an arc from the third word, which is the word had, to the word news, which is labeled subject. And finally, and this is the only thing that make these special as far as sort of mathematical tree structures, is that we have a total linear order on the nodes given by the word order of the sentence. And this will become important as we start talking about projectivity and non-projectivity later on. Now, notation-wise, I'm going to represent arcs as triples, where the first word is the head word, the last word is the dependent word, and the thing in the middle is the dependency label, so like subject and object and so on. And so I should have said this before probably. There's one other thing that is special. So by convention, we add an extra node corresponding to a dummy word, which we can call root, and which we again by convention typically prefix to the tree, and which will always be the root of the tree. So that simplifies a lot of things. And this word will be numbered 0 in the examples later on. Okay, so a transition system consists of two things. It's a set of configurations, or parser states if you like, and it's a set of transitions that can take us from one configuration to the next. Okay. So in this simple system, a parser configuration consists of three components. So we have a stack of partially processed nodes or words, and I'm going to draw the stack with the top to the right. So what you have there in the picture is a stack where the ith word is on top of the stack. Okay. We then have a queue or buffer of remaining input nodes or words, and that will be drawn with its head to the left. So we have there a queue with the jth word at the head of the queue. It's the next word to be processed. And the third component is a set of labeled arcs representing the structure that we built up to that point. Okay? And we initialize the parser to a configuration where we have only the dummy root word on the stack. We have all the nodes corresponding to the real words of the sentence lined up in the queue, and we have an empty arc set because we haven't built any structure yet. Okay? We then terminate whenever we reach a configuration that has, again, only the special root node on the stack, an empty input queue, meaning that we've consumed all the input, and whatever set of arcs we have accumulated up to that point is the output of the parser. And it's going to, the system I'm going to show you on the next slide is such that it guarantees that this is always a tree. More precisely, it's a projected tree, but we will come to that. So in this, yes.
So the way you set it up, I understand it to mean that the stack has some entries S.
Yes.
Q has some words W.
Yeah.
The arcs A, the words WI, WJ that appear in A are neither in the queue nor in the stack. In some sense, they've been processed already.
No, actually, that's not true. I mean, that's so. The arcs involve words that can still be in the stack and even in the queue, but then they have to be at the head of the... No, sorry, not in this. Sorry, I'm confused. No, okay. The words that are involved in arcs can still be on the stack, or they may have been removed from the stack.
Okay, so I guess what I'm thinking is that if the stack has, let's say, 3 nodes in it, there is no arc between them in A.
That's correct. That's correct. Yes, exactly. Exactly.
At
Yeah.
most one of WI, WJ is in S.
Yes.
Okay.
Right. So I think this will be...
And all the nodes on the queue are later in the sentence than all the nodes on the stack.
Exactly. So in a way, that's why I draw them the way I do. So if you read from left to right over the stack and over the queue, you will have the words in the order in which they occur in the sentence. And on the queue, they will be, all the words that are adjacent will also be adjacent in the sentence, but on the stack they may not be because some words may have been removed. Okay, thanks for that clarification. So there are 3 basic transitions or parsing actions in the simplest system, and they are presented here as sort of precondition, postcondition rules. So the first one is left arc. And what it applies in a configuration where there are at least 2 words on the stack. Okay, and the second of these, the one to the left, if you like, cannot be the dummy root node, because then we would be building arcs going into the root node, which we don't want to allow. But other than that, it applies to any configuration. So the effect of this transition is, on the one hand, to add an arc to the arc set. And that arc has the top node on the stack as the head, and the word to the left of it as the dependent. So if you think in this arrow notation, it will be an arrow pointing to the left, hence the name left arc. Okay. The second effect that it has is that it removes the dependent end of this arc. So this comes back to, so it keeps the head word of the arc on the stack, but it removes the dependent word from the stack. If you're familiar with sort of ordinary shift-reduce parsing, it's very similar. In shift-reduce parsing, you replace a sequence of symbols by a single symbol, which is the one you have on the non-terminal node dominating those nodes. Here, instead, you replace 2 words on the stack by the single word that is the head of the arc involving the 2 words. This action also has a parameter for a label, so when we do this, we also have to choose a label. Okay. The right arc is the exact mirror image of this, where we again add a arc between the two topmost words on the stack, and we remove the dependent word, which is this, in this case will be the word to the right from the stack. And the third transition is the shift transition, which, again, if you're familiar with shift-reduce parsing, does exactly what you would expect it to do. It takes the next word in the queue and pushes it onto the stack. Okay. Now, in case you're not yet convinced that you can actually build dependency trees with these three simple actions, here's how we would parse the sentence economic news had little effect on financial markets. So on the top, we have a stack, and I hope there are sort of red brackets with the subscript S for the stack, and there are red brackets with the subscript Q for the queue. And then at the bottom, I will show how arcs are added to the arc set. Okay. So the first thing we have to do is to shift the first two words. We are then in a configuration where we can attach the word economic as a modifier to the word news using a left arc transition. And this has the effect of adding an arc to our tree, and at the same time removing the word economic from the stack because it has been attached to its head. We then shift the word had, and we attach news to had with the subject label. We shift little and effect. We attach little to effect. We shift a few more words. We attach financial to markets. And now we're in the position to do our first right arc transition because we want to attach markets to on. And we then attach on to effect, effect to had. We attach the final punctuation to had if indeed we think that is where it should be attached. And finally, we attach the main verb to the dummy root node. We have now reached a terminal configuration because we have only the root on the stack and an empty queue, and the arcs that we have added sort of build a tree. Okay. Right. So assume for a minute that we have an oracle that is a function that for any parser configuration we may find ourselves in returns the optimal action to perform in that configuration, or the optimal transition. Okay. Now, in such a world, parsing is very easy and it's very efficient. And it can be performed by this extremely simple algorithm that just initializes the parser configuration to the initial configuration. And then we have this simple while loop that says as long as we're not in a terminal configuration, that is, as long as we either have more words left in the queue or we have more than one word on the stack, we ask the oracle what to do, and then we do it. And eventually we fall out of this loop, and whatever arcs we have accumulated at that point will be the output of the parser. So, and in fact, the sort of basic idea in at least sort of old-style transition-based dependency parsing is to try to pull this off. But of course, we're living in a world where oracles are hard to come by. So what do? Well, we do what everyone else does in NLP. Sorry. Yes?
In that notation, P is a transition.
Yes.
P of C is the oracle's decision of what transition to make.
Exactly.
P of C changes the configuration.
Exactly. Thanks for clarifying that. Yes. Yes. Okay, so we do, as I said, we do what everyone else does these days. We turn to machine learning and try to approximate oracles by classifiers. Okay? So the idea is that, and I put the word linear in brackets here because in almost all the work that I know of, this classifier is in fact a linear classifier of some kind. So essentially we say that, okay, we believe that we can approximate this oracle function by the argmax. So as our oracle prediction, we will take the transition that maximizes a score, which is a linear combination of a feature vector with this bold f of c and t, and a weight vector for those with weights for those features. Now, the feature representation is a representation of salient properties of the current configuration and one of the possible transitions that we can take out of that. And as I already said, one of the nice things about this approach is that we're very free in using features. And typically this will take the form of a so-called history-based feature representation, in the sense that we can include any information from the derivation history up to that point. And crucially, of course, we introduce features over input tokens relative to the stack of the queue. Those are the kinds of properties that all parsers use. So what is the word on top of the stack? What part of speech does it have? What is the first word in the queue? And what is its part of speech? And so on. Now, in addition, and we can do this over a fairly large window of a token, including sort of n grams of words and n grams of part of speech tags. Very importantly, we can also include features over the partial dependency tree that we built up to that point. So we can ask of the word on top of the stack, does it have a dependent to the left of it? And if so, what is the label on that dependent? Does it have more than one? And so on. In some systems, this is not true of the system I show you, but in some systems we can even ask, does it already have a head? And if so, what is the relation to that head? And so on. And we can also, if we like, add features over the actual transition sequence. So we can ask, was the last action a shift? Was the last two action a shift followed by a left arc? And so on. Now, of course, in order to, what we then have to do is we have to learn good weights for these features. So weights that will allow us to assign a high score to good parsing actions and a low score to bad parsing actions. And the simplest way to do this is that we take a tree bank. So we're working here in the sort of supervised world. So we take a tree bank, and for every sentence in the tree bank, it's easy to reconstruct the oracle transition sequence. That is the sequence of transitions that you would have to take in order to build the tree that the sentence has in the tree bank. We then take those oracle sequences and construct training instances for our classifier. So basically, any configurations that occur in such a sequence, together with the correct transition out of that configuration, is a training instance. And then we can train a very simple, unstructured multi-class classifier on this to simply try to maximize the accuracy of these local predictions. As often as possible, we want it to coincide with the oracle prediction. Now, as I already said, doing it this way is can give you very efficient parsing. It's easy to show that the number of transitions that you need to take in order to build a tree for a sentence of length n is order n. It's actually 2 times n exactly. And that means that as long as we can sort of do this, perform this classification and find the oracle prediction and also execute the transition in some constant time, which is usually easy to achieve, the parsing time will also be linear in the length of the input sentence. And we, as I said, can use very rich feature representations. It turns out, yes, Jason, yeah. It turns out that there is also a drawback to this approach. Maybe more than one, but the most obvious one is that this system is very sensitive to search errors and to not only because it only ever considers a single transition sequence. And of course, if it makes, especially if it makes an incorrect transition early on, then sort of that bad decision will lead to further bad decisions, so there will be a kind of error propagation so that the parse will deteriorate. And this is a sort of the combined effect of the fact that we use the greedy deterministic parsing, where we only explore one path through the system, and also from the fact that we use this local learning. So we're only trying to learn to make correct local predictions, assuming that we're in the correct configuration to start with. And that gives us no guarantee when we sort of wander off from this path. Is now a good time to ask the question or make the comment?
So yeah, I'm just curious about the fraction of the runtime, maybe all of it, which is spent extracting features. I know that in global parsers, you spend almost all your runtime, and they have, you probably have about as many features per decision as they do, but they are choosing among more different decisions, because there's generally n squared edges.
My question is very related. I was saying that in linear, assuming constant time feature extraction, but depending on the feature extraction time might depend on the length of the sentence.
That's true. Yeah. So okay. So yeah. So it's fine. I mean, typically with the models. Okay. No. I'll actually answer your first and then Jason. So typically with the. I mean, that could be the case, but the kind of feature models that we typically use do give you constant time feature extraction. I mean, it's constant relative to a fixed feature model, of course, but it doesn't grow with the length of the sentence, so we don't have that dependency. Still, it's definitely the case. I cannot give you an exact figures here. I haven't really measured this myself, but other people have done, and it's quite clear that I mean, by far most of the time is spent on, well, feature extraction is one thing, but just doing the dot products is also, I mean, I think even that is even worse than the actual feature extraction, because you can do clever things to extract the features, and you can do feature hashing and caching and so on.
So at every step, you're comparing how many different actions. So you wrote down 3 actions, but there's also the question of the labels on.
Exactly. So it depends on the label set. So it's 2 times the size of the label set plus 1.
Which is?
Well, I mean, it depends on your annotation, but in most cases, the number of labels is something like 30 to 50, maybe. So it's about 100 classes.
The label set depending on the part of speech tags of the items.
Some people do. Some people do. Yes. No, it's. I mean, in the MaltParser system, we don't do anything like that. But some people have have applied that kind of filtering. Yeah.
So you said you can do smart things like feature caching, but can't you also cache the dot product computation?
Yeah. No, actually, you can do, and there's actually been some recent work which is not yet published on doing that, and it seems that you can actually get very significant speed ups by, and you might even, and you're essentially doing transition caching, because you know that in many of the configurations you actually only need to look at a very small number of the features to know exactly what the parser would always do in a configuration that has that. And in that way, you can just sort of memorize. So you only do the full feature extraction and sort of computation in cases where you really need to do it. Okay. So in order to find out or sort of get some idea of what this error propagation actually does, a few years back I did an empirical study together with my colleague Ryan McDonald, who's also at Google in New York, where we did a comparative error analysis of the 2 systems that had the highest score in the Connell 2006 shared task on multilingual dependency parsing, which of course happened to be our own 2 systems. So the first was the MaltParser system, which doesn't use exactly the transition system that I've just shown you, but basically implements the same approach with completely greedy deterministic parsing and only simple local classifiers to do the prediction. Okay. The other system is the MST parser system, which you may or may not be familiar with, but which instead using an exact inference. This version uses dynamic programming so that it does give you, it's guaranteed to find the highest scoring complete tree under the model. It also uses global learning in the sense that it tries to learn a model that maximizes the accuracy over an entire parse tree rather than just sort of maximizing the accuracy of local predictions. But because of that, it is much more restricted in terms of what features you can use. You cannot use these sort of features over arbitrarily complex parts of your dependency trees and so on. Now, interestingly enough, in that evaluation, these very, very different systems got, when averaged over 13 languages to the second, almost to the second decimal point, exactly the same score. And that, of course, led to the question, do these very different systems actually make the same parsing errors, or do they just make the same number of parsing errors? And as you've probably already guessed, it turned out that the second was the case. And they did, in fact, have quite distinctive error distributions. And that's what we tried to sort of describe in this paper presented at EMNLP 2007. And summarizing a long paper very shortly, we found that MaltParser was more accurate on short dependencies between words that are close together, and also on disambiguating core grammatical functions, so distinguishing subjects and objects and sort of the labeled arguments of the verb. Whereas MST-parser was more accurate on long dependencies, that probably follows from the first statement, and dependency, but also on dependencies near the root of the tree, so getting more of the global structure correctly. And the explanation that we hypothesized for these findings, especially in the case of MaltParser, was that it seems that these rich feature models are really useful for disambiguation. And it shows up in the fact that you can use these dependency tree features with labels in them is useful for disambiguating grammatical functions. So for example, MaltParser very, very rarely makes the mistake of attaching two subjects to the same verb, which is an error that you see maybe not frequently, but more frequently in the case of MST-parser. And it's also but the fact that we see this advantage on short dependencies is that they are constructed early in the transition sequence. So they are less likely to suffer from search errors and error propagation. So here is one of several diagrams that we had in that paper that sort of illustrates this. This is precision by dependency length. So on the x-axis, we have the distance between the two words. And distance here is basically the difference, the numerical difference between their positions. So a distance of 1 is actually adjacent words, okay? And on the y-axis, we have labeled attachment score. That is the percentage of words that are assigned both the correct syntactic head and the correct label. And it's based on all these 13 languages from the first Connell shared task. And what you see is that MaltParser, which is the red curve here, has slightly better accuracy on the short dependencies. It's not a big difference, but you also have to remember that this is the area where almost all of the dependencies are. Dependencies tend to be short, so it counts for a lot in the overall score. But then you also see that dependency parser degrades more when dependencies get longer, whereas MST parser, after let's say a length of 5 or 6, basically has a flat curve. I don't think we should attach too much significance to the rise at the end. The data is very sparse there. So I will come back to this in a minute. So question is, what can you do to improve on this? And one thing that people have definitely done is to use beam search and real structured prediction. So beam search, of course, is a general technique that has been used in many contexts. I believe it was first used in transition-based dependency parsing by my Swedish colleagues from Lund, Richard Johansson and Pierre Nug. And the idea, of course, is that you, instead of maintaining a single best hypothesis that you just sort of keep elaborating on, you maintain a set of k hypotheses, in this case, typically for some fixed k, okay? So the parsing algorithm is extremely similar to what we had before, but the thing is we start now with a beam, which is a set of parser configurations, but when we start, it's a singleton set that only contains the start configuration. And then as long as we have in our beam at least one configuration that is not terminal, we do the following. So for each configuration in the beam, and for each possible transition that we could apply to that configuration, we update with that transition and we add it to the beam. And then we prune the beam so that we only keep the top k hypothesis, and we keep doing this until we only have terminal configurations, in which case we return the highest scoring hypothesis. Now, this requires not just a simple classifier that tells us what the top ranking transition is, but it requires a way of scoring complete transition sequences so that we can compare their score. And in this early work, what people did was they tried to combine sort of build a global score of a partial or complete configuration system, so a sequence of configurations C0 to Cm, by doing a simple combination, typically a sum, of the local transition scores. And of course, there is no guarantee that such a combination of locally normalized scores will turn out to be a good global score of the entire sequence or the structure that is built by that sequence. And indeed, at first we saw only very marginal gains in accuracy and only with a very restricted beam size. So in some of these works you could see that going from a beam size of 1 to a beam size of 2 helped, but going from 2 to 4 actually hurt. And it seems that the problem is, and I guess sort of also we know from work in other areas that this is not very surprising, that in order to get this to work you need a globally normalized model, and the way to do that is to actually move to viewing parsing as a real structured prediction problem. And again, as far as I know, the first to do this for transition-based parsing was Yue Zhang and Steve Clark in a paper presented at EMNLP 2008. Paper that I strongly recommend. It's called A Tale of Two Parsers, and then it has a longer subtitle, where the idea is that you try to learn to minimize the loss over the entire transition sequence instead of just sort of maximizing the accuracy of local predictions, and you use beam search to find the highest. And of course the trick here is to have not only scores over entire transition sequence but feature representations over entire so what they did was to build on previous work by Michael Collins and others for using perceptron learning for these structured problems, and the way they came up with feature representations for an entire sequence is by adding together the feature vector representations of the single transitions, which essentially gives you for each sort of feature a count of how many times that feature was active in the transition sequence up to that point. But it gives you sort of a global representation of the entire sequence rather than the sort of isolated transitions. And then they then combine this with the structured perceptron, and they also use this technique called early update or early stopping that also comes from work by Michael Collins and Brian Rourke and others, where the idea, it turns out, so essentially what you do with this perceptron, as I think many of you know, when you get a sentence in the training set, you essentially parse it with your current model, and you compare the result with the gold standard result. If they are identical, you don't do anything because you're happy with the weights you have. If they're different, you update your weights so that you give more weight to the features that were in the gold tree but not in the output parse, and less weight to the ones that were in the output parse but not in the gold tree. Okay. Now, early update means that you keep track of whether you still have the correct transition sequence in your beam. And the moment it falls out of the beam, even if you haven't reached the end of the sentence, you stop at that point and you do the update and you move on to the next sentence. And apparently that is sort of crucial for getting good performance here. So now we see a very different picture with respect to using beam search. So this is a figure that I borrowed from that paper from 2008. On the x-axis, well, actually, every single curve here is a different beam size. And the lowest one is a beam size of 1, and the highest one is a beam size of 64. On the x-axis is the number of training iterations of the perceptron. And on the y-axis is this time the unlabeled attachment score on the standard Wall Street Journal data set for English. So what you see now is that we do have a big jump from 1 to 2, but it continues to climb, and we see a very substantial improvement, at least up to a beam size of 32 in this case. 32 and 64 seems to be about the same here. So in some sense, it seems that we're now getting the best of two worlds, potentially. So if we look at this parser compared to the older locally trained greedy parser, we have a parser that is a little bit more like the graph-based dependency parser like MST parser and several others, in that it uses global learning, at least in the sense that it tries to minimize the loss over the entire sentence instead of maximizing the accuracy of local predictions. And it also uses non-greedy search. Of course, it doesn't use exact inference or exhaustive search, but it does explore a larger part of the search space. But at the same time, it's also a lot like the old MaltParser system. It's still very efficient as long as you have a constant size beam. Again, the parsing complexity will be linear. Of course, it will be slower by a factor that is sort of proportional to the beam size, but you can still make it work very fast. And you still don't have any constraints from the parsing algorithm on what features you can use. So you can use the same reach feature models here. And in fact, if you, I recently, together with Yue Zhang, did replicated the old EMNLP study, and because we were curious to find out how does ZPAR, which is Yue's system, behave compared to MaltParser and MST parser. And here is the result for this precision by dependency length. And so the purple curve, it's the highest curve, is the ZPAR curve. And interestingly enough, it actually seems to be a mix of two worlds here. So if you look over at the left end here, it's almost indistinguishable from MaltParser. So it does have the same rich features, and it gives the sort of same high accuracy on these local dependencies. But then as we move over to the right, it's actually much more similar to the MST behavior here, in that it doesn't, the use of the beam search seems to sort of counteract this degradation due to error propagation, because even though the correct transition didn't have a high score locally, it may still be kept in the beam, and later on it will actually turn out to be the highest scoring sort of global representation. Yes,
So this comparison is a little odd, I'm guessing, because the set of features is not the same.
That's right. The set of features is not the same. I mean, for MST parser and MaltParser, it's obvious that it couldn't be the same, because some of the features that MaltParser used could not be used in the sort of dynamic programming scheme. For ZPAR, we could have sort of had the same features, but we actually
Break it so it only uses the MST parser.
So,
It only uses all factor features.
we could do that, but in a way, I think that would be unfair in another way, because then you're not allowing both approaches to sort of use their optimal setup. I mean,
it would just be interesting to sort of see it as a line in the graph.
I mean, you might argue that if you do that, then you should also sort of force MST parser to do greedy decoding, because after all, the other parser is doing greedy decoding.
Well, that is effectively the line that.
Sorry?
Basically, it would be interesting to see if you're using beam search at different sizes, using only the same features as MST parser, but using a greedy algorithm instead.
Yeah.
Once you get to MST parser, just to see how much of the difference.
Yeah, yeah. So there actually, I mean, in the original Zhang and Clark paper, there are comparisons like that, because I mean, the two parsers that they refer to in the tale of two parsers is actually a sort of one that tries to mimic MaltParser and one that tries to mimic MST parser using the same features but using beam search instead. And I think they get at least very close to the MST parser results in that paper. Okay, now interestingly enough, it turns out that when you're using global learning and beam search, you can not only sort of keep the benefits, it seems you can do even better, because you can use even richer feature models. So the left column here, the one with the heading ZPAR, comes from a paper that we presented at ACL last year. It was a study I did together with Yue Zhang, where we took, the baseline here is basically the Zhang and Clark parser, or one of the Zhang and Clark parsers from 2008. And then we kept throwing more and more features at it. And some of these features are features that would be very, very expensive to use in dynamic programming, like the valency set features. We'd look at the set of all dependency labels of some dependent of a word, which sort of, and so on. And what you see here, I won't have time to go into the exact features, but the sort of, the main message here is that when you keep adding more and more features, some of them are the so-called third-order features, are sort of basically taken from third-order graph-based parsers. You seem to be getting an incremental improvement here.
So this means that you don't have that sum over f of ci minus 1 pi in this case, because some of the features aren't just for a particular I, but span larger
No, they're still over a single configuration.
Okay.
So yeah, that's a good clarification. So when I say it's a set of labels of of some dependence of a word,
Right.
it's up to that point.
Okay.
So in the next configuration, you may have added another label. So it's not globally for the output tree or anything like
They
that.
have some in the sense that a bigger set will be another feature.
Yes, yes. Now, the right-hand column here is actually not in that paper, and that's a control study that we did later on, where we tried adding exactly the same features to the old-style, greedy, locally trained MaltParser system. And what you see is that they simply don't help there. And in fact, in some cases, they seem to hurt, although actually I think that most of the thing in the right-hand column is probably sort of at noise level. But it seems somehow that in order to really be able to benefit from these more complex feature models, it seems that it's a precondition that you do global learning and beam search. Okay, I will have to speed up a little bit. So everything that I've said up to this point, or the system I've described up to this point, as I said, can only output projective trees. And now I will finally be a little more precise about what that means. So a dependency tree is projective if all its arcs are projective. And a dependency arc is projective if the head of the arc dominates all the words that intervene between the head and dependents, possibly in several steps. So here's an example from English that involves two non-projective dependency arcs. So the arc from hearing to on in a hearing is scheduled on the issue today spans the word is and schedule, but neither of those words is actually dominated by the word hearing. Another way to say this is to say that the subtree rooted at the word hearing is a discontiguous part of the string. So we get a hearing on the issue is the subtree rooted as hearing. Now, dependency grammar theories generally do not assume that dependency trees have to be projective. In fact, some of them would argue that there are certain types of linguistic constructions that necessitate non-projective analyses. But many parsers do assume or have assumed projectivity because it definitely makes life easier. It makes parsing less complex and in a lot of ways. So the question is this something we need to worry about? Well, here are some statistics that you might want to ponder on. So these are statistics taken from 8 tree banks that have in common that they are what you might call native dependency tree bank. What I mean by that is that the sentences in these tree banks were originally annotated with dependency trees, as opposed to first being annotated with some other representation and then automatically converted to dependencies, which could introduce noise. And if you look in the column trees, that tells you how many of the sentences in these tree banks have a non-projective tree according to the linguistic annotation. And those figures range from about 10% to over 25% for Basque. And that certainly doesn't look like a marginal phenomenon. I mean, it seems that it probably is something that we should at least think about. On the other hand, if you look in the column labeled arcs, you see that which tells you how many of the arcs in those tree banks are non-projective according to the definition I just gave. You see that it's much lower. So what that tells us, of course, is that for a given non-projective tree, there will typically be a very small number of arcs that are responsible for the non-projectivity, typically often just 1 or maybe 2. And this incidentally explains why maybe people haven't worried a lot about this, because our evaluation metrics, the one that are at least most commonly used, look at the last column, not at the one before. So you can still get very high accuracy scores while completely ignoring non-projective dependencies. That's an aside.
I don't understand that data a little better is you had a number for the average length of the sentence.
Mm-hmm.
So what I'm thinking is that 23% of the trees have dependencies that cross the check, and 2% overall. If I then knew the average length of the sentence,
Okay.
how many percent?
Okay. That's a good suggestion. That's definitely something that varies between these tree banks, that's for sure. So I think I will actually, this is a slide that tells you on some of the different things that people have done in transition-based dependency parsing to handle this. And that excludes all the work done in other approaches like graph-based parsing. I think I'm actually going to skip that slide in the interest of time and just talk about one approach that I've been interested in lately, which starts from the observation that projectivity is not really a property of the tree itself. If by the tree you mean only the nodes and the arcs, it's a property of the tree in relation to a particular word order. And it's always possible to reorder the words of the sentence to make the tree projective. And you can do it in different ways, but I'm picking here a canonical way of reordering the trees. So given a dependency tree with some linear order, I say that the projective order for that sentence is the order that is defined by an in-order traversal of the tree that locally, for a word and its dependence, respects the global ordering. Okay. And in the case of our English sentence here, that would give you the order that is given by the numbers here. So it essentially gives you a hearing on the issue is scheduled today, which happens to be a grammatical sentence of English. At least I think so. I'm not a native speaker. But that's not important. So the important thing is that there is always a way of reordering the words that typically involves relatively few movements so that the tree is projective. And based on this observation, we can extend our transition system by adding a single transition, which we call swap, that allows you to change the order of two words. And the way it's defined is as follows. So you actually take the second topmost word on the stack and you move it back to the queue. And the reason we do this is that we want the word on top of the stack to be the same before and after the transition. And there are conditions. You cannot do this if the word you're moving is the root node, because we don't want that in the middle of the sentence. And you cannot do it if the words are not in the original order. So you don't want to keep swapping back and forth. But adding this to our system, we can essentially perform parsing using two interleaved processes, because what this gives us is essentially a very primitive sorting algorithm, right? So we can have a process that sorts the words into projective order online as we go along, and at the same time builds a dependency tree by still only connecting adjacent subtrees. The tree that we build will always be projective with respect to the projective order. I mean, that sounds like it should be right. But it may be non-projective with respect to the original word order. So again, just to convince you that this is possible, here is how we parse the sentence. This hearing is scheduled on the issue today. So I'm going to skip up to this point. Okay, so up to this point, we've done only things that we could do before. But we now found ourselves in a configuration where we would like to attach the word on, which it's on top of the stack, to the word hearing. But we can't, because there are two words blocking this. Okay, so this is where we can apply swap once, twice, and then we're in a configuration where we can attach on to the hearing. And from this point on, everything proceeds just as in the original projective system. But at the end, we have actually built a tree that is non-projective with respect to the original word order, despite the fact that we have still only added arcs between words that are adjacent on the stack.
Quick question. This seems to now be ambiguous in the sense that I could have attached scheduled to is before the swap, or because I swapped them back to the queue, I can then shift them in and attach them.
Yes, yes. And in fact, there is such ambiguity already in the simple system, but it's of a much more trivial kind. So you can attach left dependence first and right dependence later, or the other way around. But it is true that adding the swap operation adds more spurious ambiguity to the system. And in fact, it's an interesting little problem in itself to, for a given sentence and non-projective tree, find a transition sequence that minimizes the number of swaps. If you have several non-projective structures interleaving, that's a non-trivial problem. Okay, so a couple of years back, I used this approach in the old-style deterministic parsing with a classifier, and I also showed in that paper that even though the worst-case complexity now goes from linear to n squared, because non-projective dependencies are so rare, and unlike some other non-projective algorithms that have n-squared time as both worst case and best case time, this system in the best case behaves exactly like the projective system. And we got some very nice results, especially on check at that point. Recently, in work that is only partially published, together with Bernd Bonnet, formerly at the University of Stuttgart, now at the University of Birmingham, we combined this with the global learning and beam search approach. And it turns out, and this is not really surprising, because making these swap decisions can be pretty hard, partly because of the ambiguity problem that you mentioned. So using a beam search and a sort of global model should be able to do much better. And in fact, when we apply this to Czech and German, these are results from the Connell 2009 data sets on the development sets. We see very significant improvement of about 3% absolute for Czech and 2.5% absolute for German, which is very significant, sort of given that we're basically starting at the state-of-the-art level here. And it actually shows that for languages where these non-projective dependencies are sort of relatively frequent, you can actually improve parsing accuracy considerably by taking them into account.
Are you improving parsing accuracy by more than the number of non-projective arcs?
Sorry?
Are you improving your numbers for the number of arcs that were non-projective was like between 1 and 2?
Exactly.
The performance is going up sometimes.
Yes. Yes.
At least that.
Yeah. So it's
Helping in other ways as well.
So it seems that by getting some of these non-projective dependencies right, we're also getting some projective dependencies right that we got wrong before. Yeah, that's the nice thing about it. Okay, do I have time for a quick?
Why don't you wrap up? We're not going to get chased out.
Okay. So when you say wrap up,
Why don't you take 5 minutes and wrap up?
Okay. I can do this in less. So one of the striking observations about dependency parsing is that until quite recently, all dependency parsers presuppose that the input has been morphologically disambiguated by a part-of-speech tagger, and this is in contrast to the best PCFG parsers that are not only can do their own part-of-speech tagging, but typically perform better, at least in terms of parsing accuracy, when they're allowed to do so rather than forced to respect the output of a part-of-speech tagger. So there's been some recent work in interest in doing joint part-of-speech tagging and parsing, and I'm reporting here on some of my own work of that. And formally it's very simple to turn the parser I just showed you into a joint tagger and parser. So essentially what you do is you add a parameter to the shift transition. So just as when we're making a left arc or a right arc transition, we have to choose a label for the arc that we're adding. Whenever we're shifting a word onto the stack, we have to choose a part-of-speech tag for that word. And that gives you a joint tagging and parsing model. Now, in order to make this work in practice, it's a little bit more tricky. And in fact, in the results that we have so far, we have not completely eliminated the need for part-of-speech tagging. So what we do is we still run a part-of-speech tagger over the input, but we don't force the tagger to completely disambiguate the input. So we allow up to 3 tags per word, and only if the tags are at most, the score of those tags are at most a certain distance away from the highest scoring tag. And based on that, we then allow the parser to select one of the tags that the tagger suggested. And in addition, you have to be a little careful with your beam, because if you just allow tagging variants and parsing variants to mix in the beam, there is a risk that the beam gets filled up with tagging variants and you don't have enough syntactic. So we keep that we control that by 2 different beam parameters. But doing this, we can actually, this is work presented at EMNLP this year, where we show that for a fairly wide range of typologically different languages, Chinese, Czech, English, German. We take this parser that has the swap transition and now this parameterized shift transition, and we manage to consistently improve both tagging and parsing accuracy for all these languages. The improvements are not huge, but of course it's a very hard baseline that we're up against here, and the nice thing is that it sort of seems to improve both tagging and parsing accuracy, whereas in many previous previous studies, it's often been the case that you can either improve parsing accuracy or improve tagging accuracy, but not both. Okay, I'll stop there. Thank you. We did have a number of questions during the talk, so it's.
So since you're in Google, it seems like the other thread they're following there is using structured prediction cascades to sort of limit the search space for these other kinds of dependency parsing.
Yes.
So would you comment on this is something that can be applied to your parsing to where you use sort of another predictor to
So in a way, I guess the work that I alluded to when I got this question about the feature extraction and the dot product, and is a little bit like that, but it's not done on a sort of complete sentence level, but it's done more locally. So when you have these cascades, you basically sort of run over the input multiple times with more and more sort of complex models. And whereas in this work that is going on, where you look at basically when you're in a configuration and you try to decide what to do, you first only look at a sort of very small set of features, and then you have a cache where you maybe know that, well, when I see these features, exactly these features, then in at least 99% of the cases I do this action, and then you just do it and don't look at the rest. And then you might like to, I think in the current model they're working with, it's not a real cascade, it's just sort of two levels. You either look at this very coarse representation or you do the full thing. But you could imagine doing it in several steps. But it would still be different in the sense that it's just done locally for every different transition. It's not like you're running several times over the input.
And then do the fine-grained paths have fancier features that look ahead at the results of the coarse grain? In other words, you've got the fine-grained, when you're making a fine-grained decision, you have fine-grained stuff to your right, but you also have all the stuff to your right, to the left, but you also have all the stuff to your right that survived the coarse grain beam.
But that would be true if you actually did make a whole pass over the input with a coarse grain, but you don't do this in the scheme that I...
Oh, I see.
Like, yeah.
Okay.
So you just use the coarse grain model to find out whether this is basically whether it's a deterministic decision based only on those features. But that's, I mean, that would be the advantage of doing it in a full pass over the input.
So you listed different classes of features that you are able to look at as you do this.
Yes.
But you didn't include, for example, looking at features of the classifier score. So, I mean, would it ever be useful to say, not only do I know what decisions were made, transitions that have been made, but I also know what the classifier thought about this tree.
And what it thought the second best choices were. And what it thought the second best choices were.
Well, that's a great question. I'm not really aware of any work that does that, except for the specific purpose of doing confidence estimation. But I mean, so that people have. I mean, one of the sort of, well, sometimes people when they get the output parse say that it would be really nice to get some sort of confidence estimate here. And then when people have tried to address that problem, then they of course make use of the classifier scores, and it turns out to be quite tricky because I mean, after all, these are sort of discriminative classifiers, and yeah, and so on. I'm not aware of any work that tries to look at that in order to improve parsing accuracy. I know that in other approaches like sort of discriminative re-ranking and so on, sort of the scores that you get from the base model and so on is very important.
Imagine that the learning would become tricky.
So I mean, I might add one thing. So in the joint tagging and parsing experiments that unfortunately I went over very quickly, so actually, in there, it turns out that using the scores of the part-of-speech tagger that you run over is important. So looking at having features over the scores and score differences between the one best and the alternatives that you're considering, that turned out to be useful.
This is triggered by the second innovation you talked about, where you had multiple parts of speech tag, and you said you didn't want the stack to be filled out with US
Yeah.
So you had a two-dimensional stack, if you will, right?
Yeah, it's not as sophisticated as that, but it could be. Yeah.
I was wondering if the same thing happens when you do non-projective dependencies. Where
Yeah.
Like, variants with one swap who's dominate the stack and the beam, and therefore crowd out things that have two swaps, because swap is sort of a So did you consider having two different beams, or k different beams with number of?
No, I didn't, but I think it's a great idea, and I think in general, I think something that we should explore more is the thing of how to align hypotheses that we are comparing when we're pruning the beam. So up until this point, people have always assumed that you compare configurations that are the result of the same number of transitions. Okay, and that makes sense for systems where all complete transition sequences are of the same length. But once you have the swap transition, that doesn't hold anymore. And even if it does hold, it's not obvious that that's always the best thing to do. And there are at least a couple of obvious alternatives. One would be always compare hypotheses that have the same number of dependency arcs in them, for example. And that would not be equivalent to the same number of transitions, because sometimes you make a lot of shifts early and sometimes you don't, and so on. Another idea would be always compare configurations that have the same word at the top, maybe not, at the head of the buffer. That is, that have consumed equal amounts of the input. And that's not equivalent to any of the other two. And as far as I know, no one has looked at that. And it's possible that we can do even better by finding out better ways of comparing apples with apples instead of.
One way to normalize would be combined with some kind of crude backward estimate, right?
Yeah. No. I think it's a lot. And in that way, what we're doing right now is relatively sort of simplistic in that respect. That we just use the scores as they are, and we sort of align. Of course, it's algorithmically. It's the simplest solution, because then you can have this loop. You have your beam, and you apply exactly one transition to each one of them, and then you prune again. But you could imagine sort of taking your hypothesis and you apply as many transitions as you need in order to get a new word at the head of the buffer, and then you compare them. Who knows?
You said use some kind of backward estimate. I was wondering whether the proponent of dynamic programming is recommending A-star search.
I like A-star search. And it's not incompatible with dynamic programming.
No.
So it's fine admitting how that great 2003 paper came.
Yeah. And there's a very interesting line of work recently on using dynamic programming for transition-based parsing, with work by Liang Huang and Kenji Sagai and Marco Kuhlmann and others. But I only had an hour, so. Thank you.